Don't you love it when the title of the lesson is the directions? So let's notice the pattern and write an expression. So basically, this is going to lay the groundwork for the next lesson when we deal with Taylor series a lot more in depth than we had previously. So n is going to start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, infinity, whatever. So when we notice the pattern, we're just going to try to figure out an expression here that will turn n into that. So when n is 0, then my output is 0. When n is 1, my output is 2. When n is 2, my output is 4. When n is 3, my output is 6. And I think we can obviously see what happens here. So this would be 2n. And it is incredibly obvious and probably not even worth writing. But I think it is at least worth saying that these are even. Duh. And you see that and I see that. But there's kind of a way that we write even and odd numbers when we're expressing it in terms of n, which are counting integers. So, counting integers. So like 0, 1, 2, 3, 4, 5. So these obviously are odd, and that's no secret, and that's not a surprise to anyone taking calculus. But if I wanted to turn a 0 into a 1, what would I do? Well, you'd add 1. I want to turn a 1 into a 3, what would you do? Well, I'd add 2, and then I'd add 3, and then I'd add 4, and then I'd add 5, and then, well, that's not going to work too well now, is it? Not with a just direct explicit expression. So what we really need to do is basically just kind of look at it. If I want to turn a 2 into a 5, well, I've got to get an odd number, so I can add 1 to my even number. So whatever it is, I'm going to add 1 to it so I can make it odd, and I'll just double what I have and then add 1. It makes it odd. So this is actually a very well-used expression for odd numbers. So I can just start cranking out odd numbers by plugging in 1, 2, 3, 4, 5, 6, 7, 8, 9 here. That's why I wrote the word odd here, just so whenever you need a list of odd numbers, this is what you do. Okay, and some of these are obvious: 0, 1, 4, 9, 16, 25, 36, 49. Well, that would be n squared, no secrets there. 1, 1, 2, 6, 24, 120. I hope you noticed the pattern on that one. Those are factorials. We've been through this. This lesson goes fast, doesn't it? The next one and the one after that deal with alternating signs. So if it starts positive, and then negative, positive, negative, positive, negative, positive, negative, positive, negative. So it's going to be -1, but that's not really it. So -1 to what power? Well, -1 to the n power. And let's make sure it's right. Because if we plugged in a 0 right here, we'd get 1. If we plug in a 2, if we plug in a 1, we'd get that. Plug in a 3, plug in a 4, plug in a 5. So when we plug in an even number, I'm not talking about turning it into an even number, but when we plug in an even number, we get positive. When we plug in an odd number, we get a negative. Okay? Well, now it's different, so this is not going to work. So what I have here is wrong, but we can easily fix it. So I just want it to be offset by 1. So we could do this, or you could also do this. It just depends on which way you want to kind of shift it, but either way, it's right. And then we get to this really bizarre, obscure one. And in case you really wanted to know the name of this one, these are called triangular numbers. Triangular. And if we're writing names, we probably could put factorial here. Factorial. And you could put perfect squares here, but you know that. These are triangular numbers, and triangular numbers basically mean that you can make a triangle out of that, generally speaking. So for example, if I had 3 dots, I could make a triangle. If I had 6, I could make a triangle. If I had 10, I could. If I had 1, that's the lamest triangle ever, and 0. But the pattern does continue. I wouldn't even call that a triangle. But the pattern does continue. You can see that I have 3 rows, 2 rows, 1 row. And see, 3, 2, 1, 0. And there's a pattern for that. And that pattern is not obvious necessarily. It is a well-known pattern in mathematics, and it's that right there. Okay, well, that's going to come in handy as we look at the next one. And the next one is basically positive, negative, negative, positive, positive, negative, negative, positive, positive, negative, negative. Okay, you get the drift. However, I say positive, negative, negative, positive. Notice this. Even, odd, odd, even, odd, odd, even. And it works out neatly like that. That's why we put these side by side or on top of the other. So this is going to be -1 to, well, if I want a positive, I would raise it to an even power. If I want it to be negative, I'd raise it to an odd power, and that's it. So this gives me even, odd, odd, even, odd, odd, even, odd, odd. So therefore it cranks out the pattern of positive, negative, negative, positive, positive, negative, negative, positive, right? Okay, so now I want the exact opposite of that. So let's just stick with what we have. I'm just going to write it and pretend like it's correct when it's really not. So we're going to put that, and then we're going to say, well, that's great, but I really want to just change the sign. So we'll put this. Okay, that's great, but let's clean this up a little bit. So this is not the most concise way of writing it. This is -1 to 1, as you know. So this will really become -1, and then n times n plus 1 over 2, and then plus 1. So this is the one that I will use for that.